Okay, so we're now heading into a discussion about alcohols. And of course, alcohols are one of the most um, ubiquitous functional groups in nature. They appear on sugars and they really are the foundation of carbohydrates, which require that alcohols. And so, alcohols and even small alcohols or small carbon oxygen combinations can have profound effect on physiology. And alcohols, of course, are an important part of our diet in the form of sugars, sugarols, and of course the metabolic breakdown of all those things. Of course, you find alcohols, and alcohols can be as simple as well, that's ethanol, but there's methanol for you. They can be very, very simple, and then they can, of course, get extremely complicated, and they form the backbone of synthetic intermediates, cleansers, cosmetics, fuels. You can light them on fire. And they are also, of course, in the form of boozy beverages. Um, and so they merit their own real discussion. And so alcohols, of course, have their own nomenclature. So we've already said this. Let's go over here. You got methanol, and that's methanol because that's a methane. It's only CH3. And then you've got ethanol, and you can probably figure out that you can just sort of extend this out to be 1, 2, 3, 4, 5, 6, 7, 8 octanol. All right, it's that pretty much sort of self-explanatory. But then when you're talking about actual systematic nomenclature, it becomes a little bit more. The priority is just something you have to remember, right? So if I were to draw a six-membered ring and put a Br on here, we could just call that bromocyclohexane, right? We call it one bromocyclohexane, but it's really not necessary. If you say nothing about a number, you just say bromocyclohexane. It doesn't matter where you put it. Now, if I were to draw a double bond here, the double bond in this particular instance, I'm going to redraw that so it's a little bit more clear. The double bond ends up taking precedence, all right? So in this particular case, it says 3-bromocyclohexene, all right? So we go 1, 2, 3, because we always start with the double bond in this particular case. And so now the bromo is at the 3 position. And we could call it 3-bromocyclohex-1-ene. So because the ene starts at the 1, but that's somewhat not necessary, I think. So we just call this 3-bromocyclohexene. Now if I were to throw the alcohol, so the alcohol always takes precedent. That's always the top priority. So now when you do your numbering for alcohols, you start at the alcohol and then you keep the numbers as low as you can. All the functional groups that way end up like this. And so now you have bromo, which is in alphabetical order, always going to be the first one. So that's always going to be the first one. It's at the 4 position. So now you've got a 4 bromo, and you got a ene group here. So that's at the 2 position. And you could call this 2-cyclohexene. And of course, you've got an alcohol, 1 all. All right. Not a very beautiful way of drawing that. Let me write it below here again. 4 bromo, 2 cyclohexene, that's not spelled right, cyclohexene, and dash 1 dash all. So this would give you a bromo in the 4 position of 2. Your parent is a hexene with the double bond being at the 2 position, so 2 hexene, 1 all. And there are lots of examples that you can brush up on your own. There are some traditional names for alcohols. In fact, alcohols actually have quite a few traditional names. One that I will pretty consistently refer to is if you have a benzene ring with an alcohol on it, this is called phenol, because just a benzene ring is sometimes called a phenyl. So if I say this and I say, oh, look at that. Well, in fact, I can get rid of that. chlorhexate ring and just call it that, I'd say, yep, that's a phenyl, and as in phenyl, P-H-E-N-Y-L, so this is a phenol. Phenol. All right. So what are alcohols? What are some of the things that they do? And I think if you have noticed that alcohols are very miscible in water, at least the shorter chained alcohols are miscible in water, ethanol and methanol, as opposed to ethane, which isn't miscible in water in any way whatsoever. So how does the addition of this little OH suddenly make ethane go into water so nicely? And there are actually two distinct physical properties of alcohols that account for their behavior. The first one is this wonderful dipole. So if we come back down here and we can say alcohols, wrong marker, alcohols have a dipole. All right. And that dipole comes from inductive effects. So there's a lot of inductive effects that occur in an alcohol, and that stems from the fact that electronegative oxygen can pull electron density towards itself, both from the carbon-oxygen bond and from the carbon-hydrogen bond. And you end up with a dipole on the order of 1.69 dpi. And so we usually write dipole as a little Greek letter mu there, and the high dipole interaction actually gives you pretty strong affinity for each other because dipoles attract other dipoles and dipoles attract water. And so because they have such high affinity for each other, alcohols have a very high boiling point relative to their parent molecule. So ethanol, obviously a liquid at room temperature, ethane, obviously a gas. So the addition of that one little OH makes quite a bit of difference. There's also another big difference between these two, and that is in dipole-dipole interactions that are hydrogen bond. Excuse me, the dipole-dipole interactions are relatively weak, but you can form long hydrogen bonds or hydrogen bond networks between alcohols. So you remember alcohols have two lone pairs and then they have this OH, right? And so that lone pair can actually interact with an H of another alcohol. And that lone pair can interact with another H of another alcohol. And these two H's can interact with both pairs of another alcohol, and so on and so forth. And so you end up with this pretty extensive network of hydrogen bonding. And hydrogen bonding, of course, is not a terribly strong bond. It's 4 to 5 kcals per mole. So if we were to say, you know, that's 4 to 5 kcals per mole, that's 4 to 5 kcals per mole. Just to keep you in the loop, that covalent bonds, the OH bond itself is worth 100 kcals per mole. So the little H bonds that you form here and elsewhere, these little things right here, you know, they're individually pretty small, but you can imagine that, you know, 4, 8, or we would say 4 to 5, let's make it easier for me, 5, 10, 15, 20, relatively small number that I've actually illustrated here, but, you know, I could keep going. I could draw another H bond out here, another one out here, right? I didn't even bother to do these. And you can see how that very quickly starts adding up. And so if this little alcohol wanted to scram, it's going to have to break a bunch of hydrogen bonds associated with it. And granted, all of them are small in energy, but together they add up. And so alcohols tend to have a pretty high boiling point relative to their parent compound. Now, this hydrogen bonding network actually makes for some solubility. It provides the solubility that I was talking about. Why there is these alcohols, at least the ethanol and the methanol, they tend to go into water up to a certain point. Eventually, the hydrophobic chain of the alcohol can start to predominate and they won't dissolve in water. But you can see, you know, if I start extending this, right? So this component, so let's just draw 1, 2, 3, 4, 5 hexanol here, right? So this is an example of hexanol, and you've got this area that's quite happy to start interacting with water. All right, so you've got OH, H. All right, and so there's this entire area here on the alcohol end that can actually, in fact, I can make all of these hexanol the way I've drawn it, is that you have what you can start forming are these long chain alcohols. And these long chain alcohols actually do a great job at trapping water inside of them. So you can have a bunch of water out here, or a bunch of water within this little nexus, but it starts to form this hydrophobic greasy region out in here. So that's grease, right? So this is hydrophobic chains. Hydrophobic chains only want to be next to each other. And so if you imagine what these start to look like, where you have the hydrophobic chains start to point inward because the hydrophobic chains don't want to really be associated with water, and then the alcohols start to form out. So these are all the OHs, and this is bulk water that they're all facing. You start to see what the basis of detergents are, and why alcohols make such great cleaning products as well, is you can have greasy bits of dirt or greasy bits that can get trapped. So, you know, you've got like grease. That's the country. I'll just draw a little splotch for grease. And that greasy bit can get locked inside of this hydrophobic center, while this little, what's called a micelle, a little detergent micelle, can stay stabilized in the water while it helps clean stuff up. And so alcohols actually have a pretty wide variety of uses. Now, it's difficult to really discuss alcohols without kind of getting into the fact that they're also a beverage, or at least they're found in beverages. I don't think anybody should drink neat alcohol. That seems irresponsible and bad, but who am I to tell you what to do? I'm not. You learn to make your own mistakes in life, although that would be a pretty tragically stupid one to go drink pure alcohol. But we have developed enzymatic machinery to break alcohols down. Alcohols being detergents, they can wreck the body. And you naturally produce alcohols through digestion and other things. And you don't really want to have these things. Your kidneys will excrete them and all of that sort of stuff. But the fate of alcohol is actually usually the breakdown. It's an oxidative product. So alcohols being a pretty good detergents. They're not necessarily something your body wants to keep around. They tend to dissolve cellular membranes, and so an enzyme called alcohol dehydrogenase turns this alcohol, it oxidizes it into an aldehyde. All right, specifically acetaldehyde. All right, acetaldehyde. Okay, and this stuff is responsible for hangovers. So after you've had this stuff, which is fun, this enzyme, which is a buzzkill, this stuff makes you puke. All right. And this is on its way to uh, acetic acid. So acetic acid, you know, that's just sort of a vinegar. And that is the last step. That is aldehyde dehydrogenase. All right. And this removes the acetaldehyde, which is also not good for you, until it makes um, acetic acid, which is fine. You know, there's no real problem with acetic acid. Now, of course, you probably have heard that there are ways to sort of circumvent this. So if someone were to have, say, too much alcohol or alcohol poisoning, you would normally induce vomiting to try to get the alcohol out. If you were trying to avoid acetaldehyde production, you could take paracetamol or Tylenol. So that's a competitive binder to alcohol dehydrogenase, at least in the gut. So that would keep somebody intoxicated for longer and possibly also make alcohol more dangerous. So if you were to see someone who's drinking heavily and also taking Tylenol, that might induce even more drunkenness and possibly a buildup of ethanol, which is in fact dangerous. On the other hand, it inhibits the production of acetaldehyde, which is what's responsible for hangovers. So there are obviously risks involved in playing with that biochemistry. Now, of course, alcohol production is an enzymatic process. So when we think about the consumption of alcohol and alcoholic beverages, it's a result of fermentation. And there are a number of different strains and other different little beasties that produce fermented products, bacteria and yeast among them, and they don't always do it totally neatly. Sometimes they will produce methanol, and methanol, of course, also, all these are breakdown products of sugars, by the way, has only one carbon less. And the same oxidative enzymatic machinery that utilizes alcohol will take methanol and turn it into this compound, formaldehyde. All right, so if you drink methanol, you start making formaldehyde. Formaldehyde is pretty toxic. It's actually very toxic. So proteins and other things can actually directly react with formaldehyde, and that induces a polymerization process inside of cells, which cause proteins and cellular membranes to cross-link with each other. In addition to the fact that methanol is actually pretty good at dissolving cellular membranes. So hopefully you don't go around drinking methanol. Actually, the second step is even worse. The alcohol or the aldehyde dehydrogenase will then produce formate, or formic acid. And formate is very bad for you. It causes swelling of nerves, and that can induce swelling in the eyes and the optic nerve, which can actually become damaged from that swelling process and induce blindness. So how do you treat methanol poisoning? Well, alcohol dehydrogenase has a specific affinity for ethanol 80 times high. So I should say ethanol is consumed 25 times faster than methanol by alcohol dehydrogenase. So the treatment for alcohol or methanol poisoning is actually to give somebody alcohol, ethyl alcohol, just have them drink ethanol. And that will help avoid methanol toxicity. There's also another small molecule that competitively binds alcohol dehydrogenase. The poisonous effect of methanol is not from that itself, right? Your kidneys will excrete that with mild sort of damage that occurs when you have small molecule alcohols, and that's relatively small, but it can lead to some neurological dysfunction over prolonged periods of time, which is true for any alcohol. It's the metabolic breakdown of methanol into formaldehyde and formate that actually induce a lot of toxicity and a lot of death, and can also lead to, say, impaired kidney function and from renal failure and a number of other issues that are generally unpleasant. So the specific approach there is important. Now, that is essentially that, all about alcohols. What else do you want to know about alcohols? Let's talk about the acidity of alcohols. Acidity of alcohol. So we know alcohols, if you deprotonate them, they're bases, right? So if you take, you've actually seen this, sodium methoxide. You've seen it around a lot. How do you make sodium methoxide? Well, you take methanol, and then you chuck in sodium metal, and that will generate sodium methoxide. And it'll actually also generate sodium hydride, which will decompose into hydrogen gas. And with sodium, you kind of got to be careful because you toss in a big block of sodium metal into methanol, it can light on fire. You toss in a block of sodium into water, boom, big fire. All right, the heat generated lights the hydrogen gas on fire. But it's an easy way of producing this salt. You can also use a pretty conventional base called sodium hydride. So that's sodium plus H minus. So you've seen um, hydride in the context of reducing agents. Hydride by itself is a base. H minus wants to deprotonate stuff. But if you take hydride and you attach it to boron or aluminum, it becomes sort of nucleophilic. And you'll learn more about why probably in organic chemistry too. Hydride by itself in the form of sodium hydride is basically, it's just a base. All it does is pull off protons. And sodium hydride, being the conjugate base of H2 having a pKa of about 32 means that sodium hydride, so H2 having a pKa of 32 means it's not a good acid, which means its conjugate base is an incredibly strong base. So this will deprotonate your dog, so be careful of it. It'll basically help you make whatever you want. Deprotonate pretty much any alcohol that you can come up with. And they do vary. The pKa, the acidity of the alcohol, does actually vary. And you can probably guess why. If I were to say methanol, all right, methanol looks a lot like water, and we say, water's got a pKa of around 14, and methanol then has a pKa of about 15.5. So it's a little less acidic than water. All right, see if there's a trend that emerges out here. CH3CH2OH, so that's ethanol. It's pK of 15.9, so even less acidic. So it seems like you're adding electron density in the form of carbon hydrogens, and which is explainable by the inductive and electron donating ability of methyl groups. So the inductive effect. CHs like to push electron density onto stuff, and that becomes even more pronounced when you start getting substituted alcohols. So isopropanol, for instance, has a pKa of 17.1, and then tert-butanol has a pKa of 18.0. And so you can see why. So water starts out pretty acidic relative to this. Obviously, water is not very acidic, otherwise it would burn your face if you need to drink it. But as you start adding electron density, the acidity goes down, the pKa goes up. Now, this is just a straight chain alcohol. You can actually start playing with the pKa, because if electron density pushed into the alcohol, so if I have something and I'm pushing electron density in here, and I'm doing it even better as I add more electron pushy groups like CH3CHs and carbon hydrogen bonds that push electron density into stuff. If I add functional groups that take away electron density, then you would expect that I should improve the acidity. So if I were to take, say, ethanol, all right, let's take ethanol. In fact, let me just get rid of this here. You know what? I'll keep all that. Let's just new side. We're going to move that over here. All right, so let's take ethanol. Methyl, ethyl, ethanol. All right, we've already said the pKa of ethanol is 15.9. All right. Now, what would happen if I took ethanol and I just say put a chloride on it, right? Cl. So now you've got electron density that's starting to move that way because the chlorine is more electronegative, and so it's going to start sucking electron density out of that bond. Now the pKa drops, 14.3. If I went even further and did ethanol, alcohol, and then I took and went just nuts. Fluoride, fluoride, fluoride. All right, these are all fluorides. Now I've really got pretty good electron withdrawing effects here. That's pretty strong, and now my pKa drops all the way down to 12.4. All right, but how close do these fluorides have to be? So in the case of ethanol, if I were to start, let's just move them away one more. So ethanol, and then we'll put it on CH2CH2. We'll put it right here. So CF3. Now I've got it one more carbon. So this is 1, and that's on carbon 2. Now it's on 1, 2. Now the fluorines are on carbon 3. And the pKa is actually, doesn't quite go back to where ethanol was. It's 14.6. So you're still getting some of that inductive effect. So the electrons in this carbon are still being pulled out here because the electrons in that carbon are still being pulled that way. Now I can say, if make that even longer. Let's do that, and then we'll put the CF3 right here. All right. And now in order for this to actually reduce the pKa from 15.9, you have a big withdrawing effect on this side, because remember, I guess I should keep my colors consistent. F3, F3, 3 fluorines on that carbon. Now you got a pretty big inductive effect here, a littler one there, and then kind of a really small one there, I would think. And then if you check the pKa by basically just checking a pKa chart, you're still not quite at 15.9, but you're getting pretty close. All right, 15.4. So even at 1, 2, 3, 4 carbons away, these fluorines are still exerting some effect, albeit not as much. And then once, of course, you hit 5 carbons away, that's just too far away to really induce any sort of inductive withdrawing effects from that alcohol. Now, not all alcohols are, of course, made the same. You can also alter the pKa through resonance, right? And so phenol is a great example of a pKa, of an alcohol that has actually a really low pKa compared to these alcohols. Phenol has a pKa of about 10. All right, so that's one of the lower pKa's for an alcohol, and you can imagine why, that if you were to take a base, all right, so if we were to throw in sodium hydride, which is way overkill for this thing, you can deprotonate that with a stiff breeze, really, then what you would end up with is an O minus, and you can see that I can now put that minus on, say, that carbon. All right, so what does that look like? Now I've got a resonance form that now puts a double bond here, ketone group there, and a negative charge. All right, and I can actually push this negative charge around to put a, oops, no, that's good, red. Make that a double bond and turn that double bond into a minus charge right on that carbon, right? So now I've got another resonance form here where I now have my double bond. That hasn't changed. That ketone is there. I've now got a double bond there. Now I've got a negative charge on that carbon, all right? And I can do that one more time. So you can see that I can actually keep pushing this negative charge around, and I can really distribute it. And that sort of chemical communism enables a pretty acidic proton there. Now, we had talked about alcohols in the biosynthesis very vaguely. And this is an organic chemistry course, and as much as I love biosynthesis, we need to talk about organic preparations of alcohols. And we know a couple already, to be completely honest. So where do alcohols come from? Well, when a mommy and daddy alcohol love each other very much. No, I'm just kidding. So the synthesis of alcohols, there are a number of ways actually to make alcohol synthetically, way more than I can cover here, but these are the ones that you need to know. All right, so if you start off with methanol, which we will do somewhat frequently, and this is methanol here, and just we'll put a bromine there. You know that all I have to do really is throw in some base, sodium hydroxide, and that base, being what that base is, or a nucleophile as well. And there's really not much that's going to be able to protonate, but it can attack in an SN2. In fact, let me just make that really obviously an SN2 type fashion, kicking that bromine off. All right, and that is a direct route to alcohol formation. Okay, and so you end up with HO, and albeit there's no inversion of stereochemistry because you never started with any, but it's an SN2 reaction, so you may well have thought that possible, and it is. And then you learned a bunch of different reactions for the production of alcohol, all right, from double bonds. So if you start off with a double bond here, you could say, if you wanted an alcohol through oxymercuration, there's one. That's mercury acetate. And remember that one? Huh? That's a good one. Followed by, you got to get that mercury off, which you do in the alkene case. So you're going to use sodium borohydride to do that reduction, and that will give you an alcohol. Oh, what is that? Ignore that. An alcohol right here. All right. If you did the same thing, let's say you did it with KMNO4. Everybody remembers KMNO, potassium permanganate, KMNO4. All right. And this is going to be KMNO4 with sodium hydroxide, right? Sodium hydroxide doesn't allow it to cleave in the alkyne case. You can also do it with osmium. Oh, it's element. It needs to be a small s. Osmium tetraoxide. It would be wrong if that s was capitalized, all right? Because that's not how you write that. And hydrogen peroxide, because you need to get the osmiate esters off. Then that doesn't give you one alcohol. It actually gives you the diol. So you get the alcohol and the alcohol over here, and that's the diol, and then your two methyl groups are down here. Okay? Now alcohols, in the case of alkenes, those can actually be made, unlike alkynes, those can actually just be made in the presence of H plus in water, right? And that gives you the same output as oxymercuration on the other side, right? This gives you the what we'll say is the Markovnikov product, the substituted one. Okay. Now you're going to get the anti-Markovnikov product if you go over here, and then you use BH3, the boring ether. Sometimes has a THF adduct, and then you have to add a little H2O2 in the presence of base, and that will give you the anti-Markovnikov product, remember? Oh, H, because the hydride actually from the BH3, that's the thing, that ends up here, right? So from the hydride. And then you get your alcohol there when the sodium hydroxide, or I'm sorry, the hydrogen peroxide comes and knocks off the alkyl borate. And last but not least, you can use an organic peroxide. So we just call it RCO3H, right? That's like O, oxygen, oxygen, hydrogen, and then, you know, sometimes it's like that, and sometimes there's even a chloride in that position or something. And that will give you from the inner, oh, you also need a little water, give you the di-substituted product as well. Except I've drawn it here because it does give you this trans substitution, unlike permanganate and the osmium tetraoxide, which gives you a cis addition, right? And that is what you would end up. You can also get alcohols instead of starting from the alkene. You can start from say a ketone. You can start from something more oxidized and then attack it. We had discussed this way in the beginning of the semester, that if you start off from a ketone and you have a nucleophile, and that nucleophile goes and it attacks there, it'll kick the electrons up here, right? And just as a refresher, what's happening here is you've got a carbon that's going away and a carbon that's coming out at you, and then you've got a pi bonds associated here. Well, you got a sigma bond to the oxygen, but there is a pi bond here as well, and that has pi electrons. And the nucleophile, in all these cases, comes in and attacks the pi system and kicks those pi electrons up onto the oxygen. All right, and so then what you end up with is a little bit down, and then that comes out here, and then you end up with that down, and then the negative charge, and then the nucleophile comes out here. Right? The nucleophile can come from either side. There's really no difference whether it attacks from the top or the bottom, so you don't necessarily get stereospecificity out of this, but this is what you end up with, is a nucleophile attacking the pi orbital, kicking an oxygen and making that negatively charged. And if, you take this and that's a laser pointer, and you add a little bit of acid, it's a part of your workup, you end up making the alcohol. So then you have whatever your nucleophile is attached here, whatever that is, and an alcohol. All right, and so that's one way that you can make an alcohol. We had hit on this idea a little bit with using reductants. So basically just smacking one of these, say, reactive centers with a hydride, right? So if you have say, a reduction process, so a reduction is going to bring in some electrons here. So if you have a ketone and you add a reductant, like aluminum hydride. All right, and I've drawn that as a capital L. Oh, that's a mistake. It's aluminum lowercase. Now remember your periodic table, right? Aluminum is just below boron, which means aluminum doesn't want 4 bonds. It wants 3. So aluminum is negatively charged, and you throw in this negatively charged. This comes as a salt, and there's usually a lithium charge somewhere up here. And that lithium is pretty important, okay? So you can buy this. It comes in a can. It's called lithium aluminum hydride, right? Lithium aluminum hydride, LAH. And what LAH does is it provides a source of hydride, and hydride in this particular case isn't going to be a base. It's going to be a reductant. So the hydride is actually going to end up being a nucleophile. And you'll find hydride as a nucleophile when you use aluminum or when you use a boron as its source. And basically, what you really need is something to hold on to that oxygen, and that comes from the aluminum or the lithium. In this particular case, sits there and holds on to that oxygen. That makes this really, it starts to really polarize that, right? Because this is a plus. So that's like, oh, my electrons. And then the electrons are like, oh my God, my electrons. And then aluminum hydride is like, I actually don't really want all these electrons. And they do come with a hydrogen, though. And the carbonyl is like, whoa, I don't care. And so the aluminum, the hydride, H minus, attacks the pi bond, kicks that up there. That makes everybody happy, right? Because now you can have aluminum, and it'll have 3 hydrogens, and that's cool. The lithium, for some weird reason, now this has got a hydride coming off of it, right? So, and now that's an O minus, and the lithium is still, of course, attached. So it's a lithium oxide, an alkoxy lithium salt, which that's easy enough to get fixed. You just throw in some acid, H+, and then you get your alcohol, all right? So a ketone group, which is what this is, ketone, can be turned into an alcohol, a secondary alcohol, right? So this is, should be quite specific right here. CH3, CH3. So that's a secondary alcohol. And that, yeah, you end up with an alcohol like that, isopropanol, from lithium aluminum hydride reduction. All right. You can do the same thing with an aldehyde. All right. So it's not just a ketone, but if you took an aldehyde, you would actually end up with then the primary alcohol. So again, you would have your hydride, and I could probably do a bit to show you what exactly is going on here, these hydrides. All right, these hydrides are going to attack here, and then that's where you get this H. The hydride is acting as a nucleophile because it's being aided and abetted by a lithium here. Does the exact same thing down here, H minus from LAH comes in, attacks here, and then you end up with a primary alcohol, okay? So now you have an O minus, and then your new H down here, and you have your old H right here, and so that gives you a primary alcohol. Acidic workup, of course, with H plus will actually allow you to have, in this particular case, ethanol. All right, a primary alcohol. So in essence, the reductions are adding hydrogen to both ends of the carbonyl bond, I guess. And both the carbon and oxygen, the real double bond, are bonded to a new hydrogen. All right. Now you can do the same thing with sodium borohydride. All right, and so sodium borohydride doesn't have that, super strong lithium, and aluminum isn't as tenacious as boron, but the same principle applies. All right, is that you have a ketone, and then you have borohydride, and you know how borohydride works. You've got a boron, and that boron I put on backwards. You got a boron, and you got a hydride here, and you can just see how this is going to work. You've got a boron, a bunch of hydrogens, and then that's going to exchange there. The hydride forms there, and you end up with something that sort of looks like this. There's a sodium, but the sodium doesn't play so much of a role in this particular case as the lithium or the aluminum really did in the last particular case. So you end up with an oxygen with a BH3, and the hydride that came from here is now on here. And you produce with an acid workup. The BH3 is happy to come off if you can turn this into an alcohol, and you get the same thing. This case, sodium borohydride and lithium aluminum hydride are basically the same. So you can say sodium BH4 and LAH take ketones to alcohols. They also take aldehydes to primary alcohols, okay? So secondary to primary alcohols, they share a lot of the same chemical reactivity. Now, sodium borohydride is actually a much milder reagent. So you can use sodium borohydride in water. You can use it in all kinds of alcoholic solutions. If it finds a ketone, it'll turn it into an alcohol. Lithium aluminum hydride, it's a little wild, right? I told you hydride's a base, and lithium aluminum hydride is quite happy to go and be a base. It only works if you have no additional alcohols, all right? So you cannot use lithium aluminum hydride in methanol or anything like that. That might be an important thing for you to know. The one good thing about lithium aluminum hydride, though, is that it can, unlike sodium borohydride, lithium aluminum hydride can do the same thing to carboxylic and reduce a carboxylic acid. So you can actually start off with a carboxylic acid and go to, in this particular case, there's 2 carbons, and so that will become an alcohol. So lithium aluminum hydride can, and it's the only one, reduce a carboxylic acid into an alcohol. In fact, it's so nuts, it can reduce an ester. So that's one of these things where you have 2 carbon, 2 oxygen, and that CH3 here, right? That will also, in fact, I don't need to redraw that. That makes the same thing, ethanol, all right? So you end up with 1, 2, ethanol, and then, of course, you actually end up with a methanol right there, too. But the starting material that you end up with is methanol. So if, to summarize, I can actually summarize this pretty well. If I take a ketone, right? So that's acetone, and I throw in LAH, and I throw in proton, so acidic workup, or I do the same thing, sodium borohydride, and I could do this in anything. I could just throw this in methanol, CH3OH. I would end up in this particular case with the secondary alcohol, and I would end up on that particular case with the secondary alcohol. And if I did this with the aldehyde, which aldehydes are usually pretty easy to reduce. They're actually easier to reduce than um, the ketones. So if I took the aldehyde, treated it with the same conditions, I would end up with the alcohol, the primary alcohol. Now if I came over here and use sodium borohydride and whatever solvent suits me, I would end up here with a primary alcohol as well, same exact product. And where it falls apart, where sodium borohydride really doesn't work anymore, is if I have a carboxylic acid or if I have an ester. All right, and then I take sodium borohydride with that one, or I do sodium borohydride with that one, and let's bring that down just a wee bit, okay? None of these would work. That would be no reaction, and that would be no reaction because you don't have any reactions with sodium borohydride on acids. They're just not potent enough. Whereas lithium aluminum hydride, the gangsta of reducing agents, will give me my product that I want. In this particular case, I guess that would be an ethanol and an ethanol. Okay? So that would be very convenient, which also actually, in some ways, this is helps you be selective, right? So if I have a big molecule that has multiple functional groups, let's say I found this in a cupboard. I needed one alcohol on this. I needed to make 1, 2, 3, 4, 5, five. I don't know why I would need to make 5. 1, 2, 3, 4, 5. Oh, CH3, right? So I wanted an alcohol on just one end and not both ends. I could just throw in sodium borohydride. And of course, I could do this in methanol. And the sodium borohydride would only reduce that. So I would end up with my alcohol, and my ester would be fine. All right. Or if I wanted to just reduce the whole thing and end up with a symmetrical alcohol, so I wanted the alcohol, again, with 1, 2, 3, 4. Always count your carbons. 5 OH, at least I think. 1, 2, 3, 4, 5. Yep. That's easy. LAH first, and then do an acid workup. And you get your symmetrical alcohols. Now that's essentially the story of alcohols. They do have, if you look at the periodic table, a funny little atom underneath them called sulfur. And so the chemistry of thiols is pretty similar to alcohols, except thiols have a big D electron orbital, which gives them a bunch of crazy sort of chemistry that they can do. Thiols, of course I'm talking about SH, are more acidic versus OH. So the pKa of a thiol is actually about 10, whereas this is I don't know, 16, somewhere around there. So you can deprotonate thiols much more easily. And you'll remember they're not even very good bases. Great nucleophiles, trash bases for the most part. And you can kind of see why when you look at the pKa of these two things. Thiols can do hydrogen bonding just like everything else. And thiols are great nucleophiles. And that increased nucleophilicity allows them to form pretty strong salts. So you can actually go from your thiol ether. So if you form a thiol ether, which is actually pretty easy to do, you just start off with an SH, and you toss in, say, CH3I. That attacks that right there, and you end up with something that looks like this. All right. Now, it doesn't necessarily have to stop right there. If there's an extra CH3I in there, it'll go and attack that, and you can actually end up with positively charged sulfonium salts. All right, so sulfonium salts, they are pretty crazy in their reaction. Now, alcohols, that they can do the first bit. You know, if you throw in some CH3I and some base, because you should deprotonate that. It does need to be deprotonated in order for that to react. You can end up with this methyl ethyl ether. Right, so that's an ether. It's an oxygen that's got no hydrogens. It's just carbons. Then that's it. That's the end product. This oxygen is no longer reactive, whereas this thiol ether is until it gets to the sulfonium salt. Sulfonium salt. All right, so that sulfonium salt is right there. Actually, sulfonium salts are somewhat reactive themselves, and so if you have a nucleophile negative charge here, it can actually attack that methyl group, and this whole sulfonium bit actually can be a leaving group. So if you see an S plus, you can actually imagine that as being like a leaving group, because that can come down, and then you can actually end up with something. You can get your sulfur, your ethyl methyl thioether back, and now you've got a nucleophile attached to, that was a CH3. All right. So that's pretty neat. There are reagents that you can buy that'll help you do that. Sulfur is actually also really interesting in that if you have sulfur in any reasonable amounts of concentration, and you just add like oxygen, O2, to it, you end up with a disulfide bond. So two sulfurs will actually react with each other in very mild conditions to form a disulfide. And that actually forms a pretty strong bond. This is actually called well, let me take a step back. Where you really see this very often is in protein chemistry, right? So if you have the amino acid cysteine, all right, so you got an amino acid and that's going off there, that's going off there, and you know, you've got cysteine, SH, and two of those react, you actually form an SS bond. And this disulfide bond actually is a very strong bond, and that can like wrap proteins up. So we got a protein, right? Proteins are usually like noodles, and you got a cysteine here, and you got a cysteine here. That can actually enforce the conformation of protein, which is kind of cool because if you think about it, you know, hair is made out of protein. Your hair is made out of protein, right? So your hair, some people have a lot of sulfurs in their hair, a lot of cysteine in the hair, the protein that makes up your hair, called keratin. Some humans grow hair that is very rich in cysteine, 4 times the amount of cysteine normally found. And those people have curly hair because of this. These sulfurs come and they grab onto other keratin and they induce twisting. And you can buy something, you know, I don't have curly hair, I've never bought this, but you can buy a hair straightener and that actually reduces these bonds and that cleaves them. And then when that does that, then the proteins can sort of flatten out. So that's just a sort of an interesting little tidbit for you. That is the background to sulfurs.